in 2 minutes. Now, you notice here it has some shared memory. Each stream multiprocessor has shared memory, and it has its own instruction fetch dispatch unit, and it has some level 1 cache for instructions and for data. And in terms of this shared memory, it has 16 kilobytes of it, not that much. It also has a number of registers, and this is pretty high. It has 16,384 registers, and those registers, they can hold either an integer or a single precision float. So it's basically like 4 bytes. How are things happening here? You have a grid that launches the kernel, and that grid, you specify the number of blocks and the number of threads in each block. So what happens is that blocks start getting assigned to SMs. Okay, so let's say that there are 24 SMs, like in the Tesla C1060, and then you have 100 blocks. So you take the first 24 of them and you assign them, and then now you can have 1 block per SM, or if your block is not a memory hog and it doesn't use a whole lot of registers, then maybe you are lucky, and we'll talk about it, how you can get lucky. You know, you can have 2 or 3 blocks squeezed on 1 SM. So what happens, let's say that you have 2. You have 2 blocks, then it means that the first SM uses the 1 to 2, then 3 to 4, and so on. So once they execute those, they grab the next set of 48. Okay. Now let's focus on 1 SM. 1 SM is supposed to deal with 2 blocks. So what happens is that you have a certain number of threads in each block, and the threads get divided into warps of 32, and it is this set of 32 that at each time get executed by these 8 processors, skilled processors. Now, if you have 32 threads and 8 processors, of course, the only way to deal with it is like you break that warp and work on 8, 8, 8, 8. So what happens is that if you hit, like for instance, you execute an instruction, another one, and at some point you hit a memory request, okay? You want to grab data from the global memory. At that point, you know, that warp is parked, and another warp is activated, and it starts crunching number. And at some point, it will hit another read or write or something that makes the set of 8 skilled processors idle, and you know that warp is parked, and it goes back to the first one, and it says, "Hey, have you got your data?" Basically, and it says yes, or come back, and then it starts working on it. So it's this process of switching context very rapidly with very little overhead that makes possible in GPU computing to come up with speedups that are beyond the 12-fold ratio that we saw when we look at the clock rates, okay? Because all the time, those 8 scale processors are 8 busy guys. They are very, very, very rarely idle. And they're idle if you write code that is, you know, if you were not careful when you wrote your code. If you have a lot of reads, then, you know, they end up being data starved too, but that's not likely. It's less likely to happen than when you have the CPU. So you have 2 levels of scheduling here, because one first, at the higher level, you schedule the blocks on SMs. This is one level of scheduling. The second level of scheduling is when you schedule the warps. Okay, so you have to keep tabs on this, and therefore it's only natural that you have some limitations there, because you have to keep track of things. You know, where is, you know, that block? Is it ready to run, and so on. The limitation of number of blocks that 1 SM can handle is 8. The limitation on the number of warps that 1 SM can handle is 32. on the C1060 GPU. So you have 32 warps, and each warp has 32 threads. So basically, one SM can handle 1,024 threads. That's the best case scenario. And by the same token, one SM cannot squeeze in more than 8 blocks because it has to keep track of those 8 blocks. You know, is this block ready now? Has it got its data? Should I run it? Should I wait? And so on. So there's scheduling overhead, and therefore, you know, there's some hard constraints, hard limitations in terms of the number of blocks that you can squeeze on one SM and number of warps that can be handled by the SM. I'm going to skip this. Basically, this is the warp scheduling, and just to show here, different colors represent different warps. And here, for the green warp, you know, this is the warp scheduler. Warp 8 instruction 11. Then it jumps and it does warp 1 instruction 42, then it jumps and it does warp 3 instruction 35, eventually it goes back to warp 8 and it does instruction 12, and then it goes back to warp 3 and does instruction 35. So it all depends, you know, on data availability. Is the data ready for warp? If it is, then it starts crunching the numbers. Okay, some caveats. I told you that the flop rates are pretty impressive on the GPU, but the idea is that you have single precision there, so you have to keep it in mind. And the math is IEEE 754 compliant, but there are some exceptions. They combine multiplications and additions and such. They're working on eliminating these non-conformances. I already told you that if you want to synchronize threads in different blocks, that's not possible. It is possible to synchronize threads that run in the same block. That's okay. Okay, there's a sync threads, and then if you have 512 threads in one block, they get synchronized. But if you have block 1 and block 19, there's no way you can synchronize the threads in those two blocks because they might not even be executed on the same SM. So therefore, if you really want to synchronize all across the board, what you do, you just get out of the GPU, and then you go back into the GPU. And when you go out, then it means that, you know, all of them, they are synchronized, they are finished, and then you start again. The overhead is not that bad. Now, the important thing is that if you do this jumping out and jumping in, the good thing is that all the numbers that you produced and you stored in the global memory, or if they are placed there by the host in the constant memory or in the text or in the texture memory, if you go out and come back, they are going to be there. What's in the shared memory, that's a different story. Now, I started to talk about global, constant, and texture memory. Let's talk a little bit about the memory space. So here, imagine that this is a stream multiprocessor, the SM guy. So the SM guy has on the chip has shared memory, has 16,384 registers, and it has the instruction unit here, and it has a little bit of cache for data that lives in otherwise this device memory. Now, device memory, there is device memory that is global to the entire GPU. So remember, you have on this laptop you have 4 SMs. So on each SM you have shared memory, you have registers, and you have cache. However, there is one global memory that is associated with the graphics card, and that's 4 gigabytes on the C1060. Okay, so that's a lot of it. Now, not all of it is cached or can be cached. Of that big chunk of 4 gigabytes, there is a small part that is called constant memory that is cached. For instance, if you use pi, the number 3.1.3 3.1415 and whatever, then if you want to compute the radius